Hello guys, so I want to study cevian triangles, the magenta ones, with respect to a point P on the circumcircle of a family of rotating equilaterals. So let's stop this just to explain the components of this experiment. I have an equilateral triangle here. In fact, I have a family of blue equilaterals that is rotating about its centroid. Here's a centroid. And I'm also drawing its circumcircle, this black circle here, and its incircle, the brown incircle, which is half the radius of the outer one, if these guys are equilaterals. Now let's just recap what a cevian triangle is with respect to a point P of a reference. My blue one here is the reference. It's basically, the cevian triangle has vertices at the midpoints, or at the intersections of, let's see if I can say this right. So I'm going to be drawing a line from P to one of the vertices. So here's an infinite line, this magenta line, from P to one of the vertices. And I'm going to see where this particular line intersects the opposing side of my reference. So here's the opposing side, and I can think of this as an infinite line as well. And then I'm going to get this first vertex of my cevian right here. To get the second vertex up there, I'm going to connect P to the second vertex of my reference and see where this infinite magenta line intersects the opposing side of my reference, and it intersects over there, and I can do the same for the third vertex. So this is a construction of the cevian, and I have a dynamic family of cevians. And notice that this is well known. Since P is on the circumcircle of this reference triangle, the area of the cevian is twice the area of my reference, and in this case they have different vertex chirality, so one area is positive and the other one is negative. That's why you're seeing -2 there. But a first cool fact is that dynamically you get that -2, and of course if I place P somewhere else on my circumcircle, I'm going to essentially get the same family but out of phase, since everything here is rotationally equivalent or rotationally symmetric. Okay, so let's go ahead and bring P back to this first quadrant place here. And I'm going to turn off my construction lines now that we understand what they do for the cevian. And what we want to do in this video is actually analyze the loci of triangle centers of my cevian family. So for example, here is, before I show the locus, here's the incenter of my cevian with respect to P. And as I gyrate my family, I can quickly notice that x1 is going to be tracing out a curve. I can draw what that curve is, and I can see here if my conic detector or collinearity detector is saying anything about x1. So it's basically telling me x1 is nothing. It's not a conic when I say nothing. So this is an oval. You can see that this is an oval tangent to the circumcircle at P, and it's not a conic. So we could ask ourselves, what is this oval? And I can actually move P around, and we can see that this oval doesn't change as I move P on the circumcircle. I could also ask the question, if you forget about this first order locus, what is the x1 locus with respect to changing P? So that's another question I can ask as well. What is x1 of my cevian triangles doing for a particular equilateral, right? Of course I can now rotate my equilaterals, and I can watch the locus of x1 over all p's rotate as we expect in a rigid manner. But this is not germane to the main topic here. The main topic is, I'm not interested so much in the locus of x1 over p. I'm interested in the locus of x1 over this family of rotating equilaterals. So bringing P back to this first quadrant position without loss of generality, I notice that this locus is a very special oval, and I would love for you guys to tell me what kind of a curve this is. Okay, it's not a conic. Now miracles start happening. Let's go ahead and see what happens to the locus of x2. Oops. First thing you notice is that the locus of x2 over cevians is a straight line. Mathematica is complaining here every now and then because these cevians do go through an inversion, and let's study that for a second. What do I mean by an inversion? So let's turn off the locus for a second, and let's study this family to see what's happening to the cevians. And you can see here that when one of the vertices coincides with P, my cevian triangle becomes degenerate. And in fact, if you keep pushing this, it's going to turn into a line when, actually it's going to turn into an infinite line when that vertex is exactly on P. And then once that's passed, it goes to the other side. Okay? So it goes to the other side. So we have this inversion going on here of the cevian as one of the vertices passes through P. But the interesting thing is that the locus of X2 is nonetheless a line. And if I vary P, of course, everything is rotationally symmetric. This line is going to be just going around and enveloping a circle, which I'm not showing here, but the envelope of this set of loci, of straight line loci, must be a circle by symmetry. Okay, all right, so what's the next observation here? Let's look at the locus of X3, also a line. Oops, keep hitting the wrong button. This stays in X3. Actually, what I want to animate are my cevian triangles. And you can see here that X3 is also a line. Nice. How about the orthocenter? Let's place X3 over here. You get a first very neat observation. Over the entire family, the orthocenter is stationary at the common centroid of my original family. Well, that's pretty neat. I wonder if this has an easy explanation. This is so harmonic that I think it's probably an easy explanation. I'm not worried so much about the proofs. Right now I'm just actually trying to go over the phenomena. But I very much would love to have any of you guys contribute proofs to these phenomena. Okay, all right, so I go to X5. I got a line as well. So now that we know X4 is stationary at the center and X2 is a line, right? Here's X2. X2 is also a line, as we saw. Any point on the Euler line, which is at a fixed linear combination of X4 and X2, if you will, X4 being stationary at the center and X2 being a fundamental line here. Any other point on the Euler line is going to just be at a fixed linear combination of X4 and X2 is going to be a straight line as well. So of course X3 is a straight line as a corollary. X5 is also going to be a straight line as a corollary, and you can probably draw X20, which is going to be distal, and you can say, oh, X20, which is also on the Euler line and is at a fixed linear combination of X4 and X2, is going to be a line as well, right? So here's the X20 locus, go back to the X5 locus, etc., etc. Okay, now what happens to X6? Let's look at X6. X6 is quite an interesting case. X6 turns out to be what I'm calling an inherent conic. Okay, it's an inherent ellipse. In what sense? In the sense that anywhere I place P, right, I'm going to get an ellipse. So it's telling me here that this thing is a conic. It's actually an ellipse with semi-axes 0.1 and 0.22361. So 0.1, if you, I forgot to say, but the radius, the circumradius of this family, I set it to exactly 1. So what this means is this is 1/10 of the circumradius of my equilateral family. So I have this sort of canonical locus of X6 in the sense that it's connected with an equilateral. So think about, right, the mathematical age-old question, are mathematical objects, do they pre-exist or are they discovered, right? So you could say that as soon as you define the concept of an equilateral, which might be a pre-existing concept, the concept of this conic having one of its semi-axes be 1/10 of the circumradius of the equilateral is pre-existing. I don't particularly subscribe to that theory of pre-existing mathematical objects. I actually think that objects, they go into existence very much at the time that you design an experiment to uncover them, or you actually describe them. So here we are describing a locus, which is an ellipse, which derives from a very specific construction, right, which we have gone over already. I'm going to take a family of rotating equilaterals. I'm going to designate a point P on the circumcircle, and I'm going to look at a particular triangle center of the cevian with respect to that point P. So once you specify a construction and you observe it, it's like the Heisenberg theory that measurements get affected by observations. Once you design a construction, you define a construction, you specify it, and you observe what it does, that object has magically come into existence. It didn't exist anywhere. There's no golden book of mathematical objects that say that this ellipse should exist anywhere. But once we specify everything, we notice that this ellipse is inherently associated with the circumcircle of an equilateral in the sense that one of its, the minor semi-axis is 1/10 of the circumcircle, and I would love to have some algebraic expression to determine what the major semi-axis of X6 is. Okay, let's go over a few more items here on my script. I actually want to now fast forward to X13. X13 is a very curious point because over the triangle family, so what is X13? X13 is the Fermat-Torricelli point. It's actually stationary. So I can place my point P anywhere, and X13 is stationary. So that's very nice. How about X14? Let's go to the second, I think it's called the second Fermat point. What is X14 doing? It's a circle, tangent. Let's increase the, if I can, let's increase my, yes, my sampling here to 1 degree on my locus sampling. This is also a circle, so not also a circle. X13 was a point, X14 is a circle, and its radius is identical to that of my equilateral circumcircles. So here's the family of X14. Quite nice. And it's tangent to the circumcircle at P, and I can see here that its radius, or the axes of this conic, are 1 and 1, so it's a circle, and the radius is identical. Again, it's an inherent property, right? But I had to specify the experiment for this object here, the locus of X14, to materialize itself. How about X15? X15 also a circle, tangent to P, with radius 1/3 of the circumradius. Quite interesting, right? And finally, X16 is now a third circle, also tangent to the circumcircle of my equilaterals at P, but containing now my family. And its radius is twice the circumradius. So its center is going to be the antipode of P on the circumcircle. So it's going to be right about here. I'm not drawing the center. I should, but I'm not. So it's going to be right about here. So let's just recap. If you go to X13, it's a stationary point on P. X14 is a circle tangent to the circumcircle of the equilaterals at P of the same radius. X13 is a circle tangent at P at 1/3 of the radius, and X16 is a circle tangent at P at twice the radius. Okay, there's many results related to this. One of them, there's a couple of things that I can do here, and I'm going to do in future videos. You can actually apply an affine transformation to the circumcircle and see which properties remain true. And you can also change the location of P to the inner circle, or actually to a variable radius circle. So a circle that would be in between the inner and the outer circle. But I shall do this in the next videos. All right, thanks for watching. I'll see you in the next video.